Isn't today an adequate day? Isn't it an adequate day outside? Uh, Before I start, I'll have the quizzes back on Thursday, I think. I'll have them graded by Thursday. I don't have them yet. And exam one, well, before that, labs. Remember, there's no labs this week. But remember, I'll be there, so if you have any homework questions or anything like that, the questions about the practice problems, feel free to bring them into any of the lab times. I'll be there and I can answer questions. But I'll be there for questions. And then 2 weeks from today is the first test. So just, keep that in the back of your mind. That's, I think, the 19th. Anybody have any questions about, I didn't assign any problems since Thursday, but does anybody have any questions from the problems I assigned before that? Okay. After today, I think you should be able to work on almost all of the rest of the problems on that 1D kinematic set of practice problems. So last time, the thing we finished with was talking about velocity. What does the sign of the velocity tell you? Yeah, the direction. So if something's moving in the positive direction at an instant, it has a positive sign. And if something's moving in the negative direction, velocity has a negative sign. Okay? And if I say velocity, am I talking about average velocity or instantaneous velocity? Yep, instantaneous. That's the one that's going to be important to us. Why did I bring up average velocity? Yeah, we're not actually going to use it to find. That's the right idea. I just used average velocity to give a definition of instantaneous velocity. So that if you're curious what the idea comes from, that's sort of where it comes from. But we're never going to use those formulas to calculate velocity. We'll use different sets of formulas. So there's only one kinematic quantity that we still have to define. What's that? So we've done position, displacement, velocity, acceleration. Yep. So the last thing we have to define is acceleration. And you can think of acceleration as telling you how quickly the velocity is changing. So remember when I defined average velocity, we chose two instants, T1 and T2, and then the average velocity was the difference in the positions at those two instants divided by the elapsed time between them. So I'm going to give you the definition of acceleration, and notice that it's like the exact same form as the average velocity. It just has a velocity in place of the position from before. So let me write it. Choose two instants, T1 and T2. And the acceleration is the velocity at T2 minus the velocity at T1 divided by T2 minus T1. So notice just as velocity tells us how quickly the position is changing, acceleration tells us how quickly the velocity is changing. Nope, they can't ever be the same number. They can be, this is just sort of like if you haven't taken a class where you've talked about limits and things, this is sort of seems like a silly distinction. They can be infinitely close together, but they can't be the exact same point. And that's the kind of thing that you get into in calculus. But for us, we can just think about them a finite distance apart. T1 is earlier and T2 is later, so T2 is a bigger number than T1. And let me just write down a list of things to keep in mind about acceleration, because acceleration is going to be sort of a hard thing to wrap your heads around. This is the first one. Acceleration has the same relationship to velocity that velocity does to position. The second one is, notice that what this looks like is the average velocity. When I defined average velocity, I said position at the later instant minus position at the earlier instant divided by the elapsed time. We're not going to make that distinction here. And the only reason we're not is the only accelerations we're going to deal with in this section are constant accelerations. And if the acceleration is constant, then the average and the instantaneous acceleration are always the same thing. Okay. So for us, the second thing here is we'll only do constant acceleration in this section, this part of the class, not in this section. Not like I'm saving the hard stuff for the other sections, you know what I mean? In this part of the class. And so if you have constant acceleration, the average acceleration is equal to the instantaneous acceleration. Okay, the third thing, this is the hardest thing to get used to. And I think the reason it's hard to get used to is, I said when we started talking about kinematics, I made that table that had the directional quantities that are important to us on one side, and then the non-directional quantities that we use in everyday speech on the other side. And so there was displacement, and its non-directional version is distance. And then there was velocity, that has direction, and its non-directional equivalent was speed. But with acceleration, if you remember, I said, the one we're going to use is acceleration, and it has direction. And what we use in everyday speech is also acceleration, but we use it in a different way. And that's the hardest thing to, that's what makes it, I think, one of the things that makes it complicated to get used to. In everyday speech, we talk about acceleration if something's speeding up and deceleration if something is slowing down. And so I think that's why it's sort of natural for people to think, well, a positive acceleration is something that's speeding up, and a negative acceleration is something that's slowing down. But that's not how it works, okay? So this is an easy pitfall. Don't think that positive acceleration is speeding up and negative acceleration is slowing down. Here's how it really works. If the velocity is equal to 0, then the object is at rest. And so if something's at rest, then any acceleration is making it speed up. You can't get any slower than stop. So if the velocity is 0, any acceleration, that's not equal to 0 makes it speed up or means it's speeding up. Now, if the velocity and acceleration have the same sign, then the object is speeding up. And if the velocity and the acceleration have opposite signs, then the object is slowing down. Yeah. This, I guarantee there's going to, at some point, be a quiz question about this. This is super easy. Okay, so if a ball is falling down from the sky, a pop fly or something, and it's on its way down, is it speeding up or slowing down? It's speeding up. What's its velocity if it's on the way down? So let me give a positive. So let's say that we'll call up the positive direction. So if it's going down, what's the sign of the velocity? Negative. So it's speeding up, and it has a negative velocity. So what does the acceleration sign have to be? Negative. If it's speeding up, the signs have to be the same. So we know that the acceleration has to have a negative sign. So even though acceleration, so velocity is something we can sort of imagine. Acceleration we kind of have to think of mathematically. It's not really something that we can wrap our heads around in the same way as velocity. But thinking about it this way, we can get a sense of the direction of the acceleration. So if you're not talking about signs, if you're talking about directions, what you know is that when the ball's coming down, its velocity is this way, right? And if its velocity is this way and it's speeding up, its acceleration also has to be this way. They have to be in the same direction. Okay. So that's really the only way to have like intuition about like, is the acceleration like this or like this, or, you know. Okay, what about, so a pop fly on the way up, it's going straight up into the air. Is it slowing down or speeding up? If like right after you hit it, it's going straight up into the air, eventually it's going to stop. So it needs to be slowing down, right? So on the way up, it's slowing down. If the positive direction is up, what's the sign of the velocity? Positive. It's slowing down, so what's the sign of the acceleration? Negative. Yep. And so this is the first time that we've seen that even though like the ball's velocity as it goes up and then turns around and comes down, it changes signs because it changes directions, but its acceleration never changed directions. That's sort of a weird thing. But its acceleration comes from gravity, which is always just pulling things straight down. And that's why the acceleration of something in free fall is always down. Okay. I'm going to try to keep emphasizing this because it's a really easy thing to get tripped up on. Yes. It depends what you choose as your positive direction. For free fall problems, we'll always choose the positive direction up. And so the acceleration will always be negative. And it's always down no matter what you choose as your positive direction. But okay, so here's an example of how this works. So let's say there's a car speeding along. I don't think cars really make puffs of smoke like that, but so this car is heading this way, okay? And let's say we make the direction that it's moving our positive direction. So first, let's say it's speeding up. What are the signs of the velocity and the acceleration? Okay, so what's the direction of the velocity? It's that way, which is our positive direction. So velocity is positive. And then what's the sign of the acceleration? Also positive because it's speeding up. So now let's say it's slowing down. So let me write this here. So velocity is positive and acceleration is positive. Now let's say it's slowing down. Again, what are the signs of velocity and acceleration? So velocity, what's the sign? Positive because it's still moving in the same direction. Just now it's slowing down, so what's the sign of the acceleration? That's right, so acceleration now has to be negative. Now let's do the same thing again. We'll imagine that we're watching the same exact thing. But now we're going to switch what we're calling the positive direction. So here's the car again. And it's moving in this direction. But now we're calling this positive. And so, like, one of the key things to keep in mind is we're just we're the eggheads. We're not actually doing any of this stuff. We just sit there and talk about all the cool stuff other people do. We don't control them. They don't care about us. You know, they're going to the prom and stuff. We're like in our bedroom, like watching My Little Pony or whatever. Okay? We don't control them. So this car is still doing the same thing that it did before. First, we'll say it's speeding up. Okay, so it's moving in this direction and speeding up, and we can't control that. But we have done something that's going to change the signs of those values, and we'll see how it'll still work together even though we've made this new choice. So if it's speeding up, what's the sign of the velocity in this case? Negative, because the car is moving opposite the positive direction. And if it's speeding up, what's the sign of the acceleration? It has to be negative also. If they have the same sign, it's speeding up. And second, now it's slowing down. What's the sign of the velocity? Negative. It's still going in the negative direction. And if it's slowing down, what's the sign of the acceleration? Yep. Now acceleration is positive. And so what's the same is, so if you're thinking in terms of signs, all our answers were opposite this time than they were last time. Think about it in terms of just pointing in the directions of velocity and acceleration. So in this case, with the positive direction this way, it's speeding up. Its velocity was this, and its acceleration was this. Okay, and let's look at the case before. The signs are different, but in this case, the velocity was this, and the acceleration was this. Okay, so if you're just, without doing it mathematically, you're just pointing in the direction of velocity and acceleration. Our choice of positive direction didn't change that at all. It just changed how we represent it mathematically, or what a positive value means. And the same thing happens with it slowing down. In both cases, the velocity is this way, and the acceleration is this way. Anybody have any questions about that right now? I mean, I don't want to act like this is a simple thing that everyone wraps their head around in 5 minutes, because this is something that's going to keep coming up, and for almost everybody, you'll think you have it straight, and then you'll get confused again, and little by little, you'll sort of iron it out. It's a tricky thing, but this idea of relating directions to signs and having the freedom to choose what the positive direction is, it's a complicated, tricky issue. Okay, so for like almost the last full class period, we've been talking about these definitions of position and velocity and acceleration, and I've even given you some equations, but we're not going to use any of those equations. This has all been just set up to give you the equation. Okay. But no, that was a perfect time for it to crash, because this is like a historic moment for 1D kinematics. That was like, we had that long pause, and now I'm going to give you the 3 equations that all of these problems are based on. So these are the equations for 1D kinematics of particles with constant acceleration. And these are there might be a problem or two where you don't use these, but for the most part, these three equations will be used in about every 1D kinematics problem. The first one says, okay, so here's like a setup first. So first I have to tell you what these things mean. P sub I and V sub I are the position and velocity at time equals 0. And position final and velocity final are the position and velocity at time equals time final, T sub F. So the first one says V final is equal to V initial plus A times T final. The second one says P final is equal to P initial plus V initial times T final plus 1/2 A T final squared. And last one says 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And so now I'm going to go through just a set of steps. I guess I have it sort of broken up into 4 steps for how to use these in every problem where it comes up. Yeah. So these are the steps for using the constant acceleration equations. So the first thing is we need to choose 4 things. Two have to do with times, and 2 have to do with positions. So I'm going to list the time ones first. You have to choose an instant corresponding to time equals 0. And an instant corresponding to time final. So let's say that's A, B, and there are right and wrong answers to these. Occasionally there's more than one right answer, but you have to get these right or you can't do the problem. And you choose these based on when you know stuff, and when you want to know stuff. So for example, if you have a problem that says a car starts at 50 miles per hour and then slows down for 8 seconds with an acceleration of this, what's its velocity at the end of the 8 seconds? Did I say 8? Then you have to ask yourself, when do I know stuff and when do I want to know stuff? Well, you were given a velocity at, there at the beginning of that problem, what you would end up calling your time equals 0. And so you want to choose, when it says you start at 50 meters per second, whatever it was. That's too fast to go in a car, by the way. Don't do that. So you choose your time equals 0 to be the place where you have that information that the car is moving 50 meters per second. And then you're asked what the velocity is 8 seconds later. So your time final is going to be at that instant when you want to have information. You have to choose those two instants to be where you have information already and where you want to calculate information. And then the second two are related to positions. You have to choose the location corresponding to position equals 0. And the positive direction. Those two choices about times are totally crucial. Like if you don't get those right, there's no way to recover from that. C and D, though, these are totally arbitrary. Those are just setting yourself up so that you're consistent through the whole problem. Arbitrary. Okay, and so you can get this problem right and have a totally different choice of the position equals 0 in the positive direction than somebody else who gets it right. The second step is list out all the variables you know and all the variables you want to find. And I guess I would say list the variables you know and a single variable you want to find. You can only find one at a time. The total, so all of the variables, the full list of possibilities is time final, P initial and P final, V initial and V final, and then acceleration. And so you can just go through this list one by one and think, am I given the value of this variable? And if not, am I asked for it? Or would I be okay never knowing it, So for example, you might have a problem where time final, that the whole thing they're describing takes 6 seconds, and that you chose your 0 position to be where the object was at time equals 0, so you know that. Oops. And the final velocity and the acceleration, and let's say that you're trying to find the final position. And then once you have your list, you want to choose one of those three equations. You want to choose an equation that includes the variable you want, and every other variable in that equation in the equation is known. If you can find an equation that meets these criteria, then you can use that equation to find what you want. And the reason it works is with a single equation, you can always solve one variable. You can't solve for more than two. You can't solve for more than one variable. So if you can find one where you know every single value except one, you can rearrange it algebraically and solve for the one variable. And then sometimes on the harder problems, if there won't be an equation that works. So if there isn't an equation that works, choose an intermediate variable to solve for. Usually that's going to be either time final or acceleration. Then go back to step 2. So the idea is, if you can't solve for the variable that you're asked for in the problem, you try to solve for another variable that isn't asked for. And now you have one more thing in your column of known values that might make it possible for you to find an equation that works. So far this is pretty abstract, but does anyone have any questions yet? I think what we really need to do is just a bunch of example problems, and you need to work on a bunch of problems, and it'll start to make sense, I think. Okay, so here's the first example using these constant acceleration equations. A car is traveling at 30 meters per second and hits the brakes. And the car reaches a stop 20 meters away. What was the acceleration? So here's the car. It's going this way. It hits the brakes here, and then 20 meters away, it comes to rest. Okay, so first we have to think about the instance where we know stuff and we want to find stuff. Those are going to be, the earlier one of those is going to be our time equals 0, and the later one of those is going to be our time final. So what's the earliest instant where we know stuff? Well, we know that at the instant that the driver hits the brakes, the car is moving 30 meters per second. So we know something at that instant that the car starts braking, right? So I'm just going to write it like this for now. Our time equals 0 instant is going to be when the car hits brakes. And then is there a later instant where we either know stuff or want stuff, or both? In this case, it's both. That's going to be our time final. So you can think of it as the instant when he's traveled 20 meters and comes to rest. Okay, I'll just write it as reaches rest. At that instant, we know that the velocity is 0 because he's stopped. And we know that the position is 30 meters farther. Well, we haven't chosen directions and stuff yet, but we know something about how far he's gone. Okay, we'll be able to use that for the position. Okay, so now we have to choose our position equals 0 and our positive direction. And those are arbitrary. We can do those however we want and still get the right answer. But normally, if there's not some other reason that jumps out at me, I'll just choose my position equals 0 to be the object's location when time is equal to 0. Okay, so my P equals 0 is going to be the car's location at time 0, or the car's location when the driver hits the brakes. And then for a positive direction, this is arbitrary too, but I'll just say it's in the direction of motion. So if we go back up here to the drawing of the problem, I chose a 0 position to be here. And I chose a positive direction to be this way. And now you can see that this looks a lot like those kind of problems that we were working on last time. We're trying to label these different points, give them numeric labels according to the distances and directions and stuff that are given and chosen. So if this point is 20 meters in the positive direction from 0, what's the position where he comes to rest? Positive 20. And so that's something we can use. We know that at time final, the position is positive 20. Okay, so now let's start listing out what we know and what we want. So this was step 1. Now step 2. So all of the variables are time final, position initial and position final, velocity initial and velocity final, and acceleration. So we'll just go through that list and think about, do we know them or do we want them? Time final. Do we know? So we specified that time final is when the car comes to a stop. Do we know how long it is, the amount of time between when the driver hits the brakes and he stops? No, we don't know that. So we can't write it here. Are we asked for it in the problem? Do we want to solve for it? No. And so if we can solve this problem without ever figuring that out, that's perfectly fine. So I'm just going to leave that off. What about initial position? So remember, that means the position when time is equal to 0. Do we know what that is? We do have that. If you look up at this picture here, the car is right here when time is equal to 0. And we know that that position value is 0. So P initial is equal to 0. Do we know the position of the car when it comes to rest? Yep. So P final is equal to positive 20 meters. That's what we figured out from this picture. Do we know the velocity when time is equal to 0? Yeah, we do. We're given the speed, 30 meters per second, but the speed is missing the directional information. So we have to take that speed and add our own understanding of the direction to it. Okay, so we know the speed is 30 meters per second. What direction is the car moving, positive or negative? Positive. And so the velocity is positive 30 meters per second. So VI is positive 30 meters per second. I just put the positive on there as a reminder that you have to, often you're going to have to supply that sign yourself. And then what about when time is at time final, when it comes to rest? Do we know the velocity of the car? 0, yep. When it stops, it's 0. And then the last one is the acceleration. Do we know the acceleration of the car? No. Do we want it? Yeah, that's the thing we're trying to find, so I'll put that over here. And now we're going to look for an equation that has A in it, and everything else that appears in it is known. So look at those 3 equations and see if there's one that works. Here are the 3 equations. Well, the first one has acceleration, so that's good, but it also has time final, which we don't know, so we can't use that, at least not yet. The second one has acceleration, but it also has time final, so we can't use that one either. The third one has acceleration, so that's good. And the other variables are P initial and P final, and V initial and V final, and we have all those. So the third one is the one that's useful to us. So we're going to use the equation that says 2A times the quantity P final minus P initial is equal to V final squared minus V initial squared. And if I plug in these values, I have 2A times the quantity 20 meters. And for now, we're going to keep all the units in our calculations. Later on, we can skip that step. But first, we're going to do it the most careful way. So the quantity 20 meters minus 0 is equal to 0 squared minus 30 meters per second squared. So if you multiply these all together, you get 2 times 20 is 40. So 40 meters times the acceleration is equal to 30 squared is 900, right? The negative is outside of the parentheses, so we have negative 900. The meters per second is also squared, so we have meters squared per second squared. And now to do that last division, we want to divide both sides by 40 meters. I'm going to set it up in that same format that I did unit conversions. So A is equal to negative 900 meters times meters over seconds times seconds. And then dividing by 40 meters is multiplying by the reciprocal, so I'll put 40 meters in the denominator. Two of these meters cancel. And 90 over 4 is 22.5. So negative 22.5 meters per second squared. Any questions about that? Okay, well, now let's think about the sign of that acceleration. Does it make sense that the sign is negative? It does, because the way we chose our positive direction, his velocity was positive, and he was slowing down, so the acceleration has to be negative. So that's exactly what we would expect. Any questions about that one? I forgot to mention that the units for acceleration are always length over time squared. And so the SI units are meters per second squared. And so by going through carefully with the units in our calculation, you can see if you do it right, this will always work out that the units that we calculated are the units of the thing we were looking for. And that's, if you always use your if you always do your calculations with your units like this, that can often be a hint that you did something wrong. If you go through it and, you know, say I would have come out with meters per second for this acceleration. Well, I know that that can't be, because acceleration has to be meters per second squared. So somewhere I made a mistake. It's possible I just made a mistake with the units and it doesn't end up mattering. But it's also possible that I went the wrong direction somewhere, and it not only messed up my units, it messed up my numeric answer too. Let's see. Let's do another one. Okay, so let's say there's the human cannonball for, what's the circus that just closed? He's soon to be unemployed human cannonball. It was either Barnum and Bailey or Ringling Brothers. I don't remember which one. One of the big ones that's been around forever. Anyways, that looks even worse. But did you know that the human cannonball is not shot out of a real cannon using gunpowder? Did you know that it would burn him really badly if they tried to do that? Okay. You know a lot about circuses. So he's on a platform here, squatting down. They put a wick on here and light it, which is sneaky, because that really doesn't do anything. But he's in here. And let's say that this thing launches him. So that platform leaves contact with his feet 3 meters after it starts pushing on him. And let's say that over those 3 meters, he goes from rest to 12 meters per second. So first, let's calculate acceleration. And second, let's calculate the amount of time that he's in contact with that platform. So how long does it take? Okay, so step 1 is to choose time equals 0, time final, position equals 0 in the positive direction. So first, the two most important ones. What's going to be the time equals 0? Yeah, it's going to be the instant when this platform starts to accelerate him. And the reason that we're going to choose that is because we know something about him at that instant before he starts to, right when he starts to accelerate. What do we know at that instant? We know his velocity is 0. And actually, now that I think about it, we know one more thing. We know it's 3 meters from where it finishes. That's going to give us position information once we make all these choices. So time equals 0 is going to be when the acceleration starts. Time final, what's that going to be? That's going to be once he's gone 3 meters. And the reason that's going to be time final is because we know the velocity there too. And we also know that we're going to know something about the position because we know that distance is 3 meters. And now the position equals 0. I'm going to do the same thing I did before. I'm going to choose my 0 position to be his position when time is equal to 0. And that means when he reaches the end of the cannon, what's the position there? If he's 3 meters in the positive, I didn't choose a positive direction yet. But let's choose a positive direction in the direction of motion. So position equals 0 is when he starts to accelerate, or let me put it like this, it's his position when time is equal to 0. And the positive direction, like last time, I'm going to choose the direction of motion. So positive direction is this way. And so up here, when his feet leave the platform, that's 3 meters in the positive direction from 0. So what's the position there? Positive 3. Okay, so step 2. List out all the variables we know and the variable we want. So I'm just going to go through the list in order. Do we know the elapsed time? No, we don't. We do want that later, but I'm going to just do it one step at a time. So for now, I'll just leave that off. Do we know the position when time is equal to 0? Yep. Pi is equal to 0. Do we know the position at time final? Yep, so P final is positive 3 meters. Do we know the velocity at time equals 0? Yep. He starts at rest, so V initial is 0. And do we know the velocity at time final? Yeah, we know that. We know that the speed is 12 meters per second. And like we'll often have to do, in this case, we have to supply the direction ourselves. So what direction is he moving? We know he's going 12 meters per second, but is he in the positive or negative direction? Positive. And the thing we want is the acceleration. This problem, part A of this problem is just like the last problem we did, and we'll use the same equation. Yes? We would need that angle if, well, we wouldn't be able to do this problem yet. We will be able to later in the class. If we were trying to figure out now, like how far he flies, we would need that angle. But all we know is he's moving in one-dimensional motion along the length of this cannon, and we're given stuff so that we don't have to calculate. We don't need the angle to calculate it. Okay, so we're going to use the same equation as before. So 2a times the quantity P final minus P initial is equal to V final squared minus V initial squared. So we have 2a times the quantity 3 meters minus 0 is equal to V final is 12 meters per second. So 12 meters per second squared. V initial is 0, so this is 0 squared. And if you distribute this all through, so I get 6 meters times the acceleration is equal to 144 meters squared per second squared. And now I'll divide both sides by 6 meters. So the acceleration is equal to, I'm going to write this as 144 meters times meters over seconds times seconds. And then divided by 6 meters. Cancel 2 of those m's, and you come out with 24 meters per second squared. Does it make sense that in this problem the acceleration is positive? Yeah, because the velocity is positive the way we set it up, and he's speeding up the whole time. So velocity and acceleration have to have the same sign. And then the second thing, I guess, you might want to think about for a couple seconds if you own a circus, is, can you survive that much of an acceleration? You know, because it's expensive having to get a new human cannonball at each show. Yeah, you can survive that. That's so 1 g of acceleration is 9.81 meters per second squared. So this is, 2.5 g's. I believe that that's a bit uncomfortable. If you have to deal with that for a long time, but for a short amount of time, like anyone can survive that. Like, I don't remember. Everything I know about like the survivability of different numbers of G's comes from like 10 minutes of a Nova special on fighter pilots I watched. But I think they like occasionally get up to like 10 G's and stuff. But then like when they're doing that, they like, like when you try to make your face turn red, they do that to keep the blood pressure in their head up so they don't faint. Okay, what are we talking about? Yes. Oh yeah, really? But 2.5 G's is still fine. Oh really? Okay, so don't go to 8 G's. Wow, that sounds really bad. Okay, well this is less. So, well, I still feel good about shooting this guy with this cannon.
So if we have the force, it pushes them at 12 velocity at 12, like that spring, them, like if we double it, would that increase the 24 then to 48?
Yes, so 12 meters per second squared means that every second the velocity increases 12 meters per second. Okay, so 12 meters per second squared, one way to think about it is that every second the velocity increases another 12 meters per second. So if you start at rest and do that acceleration for 1 second, the velocity is 12 meters per second. If you accelerate for another second after that, the velocity would be 24 meters per second. Each second it increases that amount. Yeah, so then this only works for constant acceleration. So he's in constant acceleration until his feet leave that platform. Then he starts a new constant acceleration because the only force acting on him is gravity. But yeah, he would go up for a while and then come down, and hopefully there's a net where he comes down. That's the idea. So let me stop for today, and on Thursday I'll finish this problem. We'll just keep doing examples.